Okay, regression results, always an exciting moment for any applied researcher. So here, this output comes from the statistical package Stata, which is used very widely by economists across the spectrum, as well as a couple of other social sciences, maybe some more quantitatively oriented political scientists, although I think they generally gravitate towards R. But in any event, Stata is excellent for econometrics, and there's lots of tools online to be able to learn how to use it. So here we start with this command inside of Stata, reg weight height. This means regress weight height. And this is what we want to do for a linear regression model. And the result of that gives us a bunch of information, a whole lot of numbers here, and let me just walk through a few of those. So the easiest things to start with are over here, we have the number of observations. As we talked about before, there are 13,034 observations in our data set that are included in this regression. We have an F statistic here, which tells us about the model and whether all of the parameters that we're estimating are equal to 0. It gives us this extremely large number, and the probability of that this associated with this F statistic is effectively 0, a very, very small number. What this means is that our model matters at least a little bit in terms of what that means is the height is at least something of a predictor of weight. Now, the R squared value tells you the percentage of the variation in your dependent variable that is explained by your model. Now, in this case, we have a very simple model. The only thing that's included in it is height. So we have an R squared of 0.2337. What that means is that of the variation in weight, about 23% of it is explained by height. That's actually pretty good. We know that there are so many other things that are related to weight. So the fact that height alone explains about 23% of the variation is actually a pretty high number. So let's go, I'm just going to direct you to ignore these things for now. Those of you who do more quantitatively oriented work might care about this at some point, but we're going to focus on this lower panel, which is the kind of the nuts and bolts of what we want to look at. So what we have is an answer to our question: what is the effect of height on weight? Or at least what is the relationship between height and weight as observed in this data? And we get an equation that mirrors what we had talked about earlier, with showing that y is equal to some intercept plus some slope times our x variable. So weight, or y, is equal to some intercept, in this case negative 147, plus 4.808 times height. So our slope is 4.808. In that scatter plot, if you were to plot this as a standard y equals mx plus b kind of a model like we learned back in middle school or even before, it would match that cluster of data reasonably well, or at least as well as any equation could. And that's exactly what we've done here. So here's that intercept. Remember, we said it was a negative 147. So here it is here, negative 147. And then if you were to calculate this slope, remember it's a linear relationship, so the slope doesn't change. That corresponds to 4.8. So for every 1 unit increase in height, there is a 4.8 unit increase in weight. And that's how we create this linear regression model. It's called the line of best fit. In other words, if we had to draw just one straight line to show the relationship between these two things, which one does the best job of fitting the data? And the way that this happens, just briefly, I won't go into a lot of detail about it, is by minimizing the sum of squared errors. So, but you find what Stata does is it finds the line that minimizes the amount of variation away from this line. So you take the distance between this line and this dot, you square it, and that's just to avoid getting negative values. And then you sum, and you do that for every single observation. And so Stata finds the line where the sum of all of those squared errors is the smallest it can possibly be. So if you were to take this line and tilt it, angle it a little bit differently, so maybe there would be an intercept here, and it would be a flatter line that goes this direction, it would not fit the data as well. So what this tells you is that this is the best approximation that we can come up with of the relationship between height and weight from a statistical point of view. So let's talk about what we can do with this. We can use this equation that we've just generated to predict our dependent variable y. We've got this line of best fit in the graph, and so we can basically plug and chug numbers. So if we have a height of, let's say, 5 feet, then we can figure out, well, what will the predicted weight be? So suppose we know someone's height, but we don't know their weight, and for some reason we need to try to predict it. We could put that, the way that we would do that with using linear regression is we would plug their values for weight into this equation. So you've got negative 147.10 plus 4.81 times the height. And here we've got 5 feet, 12 inches per foot. So the predicted weight would be 141 pounds. For someone who's 6 feet tall, their predicted weight would be, again, same intercept because that doesn't change based on weight, plus this slope times 6 times 12. And that total value winds up being 199. So what does the constant term mean? This negative 147 value. That seems a little strange if we're talking about height because, well, how can someone be negative 147 inches? That doesn't make any sense. Kind of the lower bound there is 0. And so this is something where it takes a little bit of just, thinking about the intuition here. So this is simply the predicted value of weight when height is equal to 0. Now, I don't know of anybody whose height is equal to 0. And so in general, the constant term really doesn't help you a whole lot when the average value of your independent variable is a lot larger than 0. And it's pretty rare actually that we even really care about the constant term. It just is sort of a level that we move up and down in order to fit the data. But what we usually care about the most is the slope, or this 4.81. This 4.81 that we're talking about. So we don't usually care very much about this constant term, except as it relates to other parts of the data set. Really, what we usually care about is this coefficient 4.81. So let's talk about marginal effects. This is where it gets really exciting. So we are looking at a change in y, which is our predicted weight, as we just talked about, for a given change in x, and in our case, height. So the marginal effect is 4.81 pounds per inch. That means that for a 1 inch increase in height, we expect a 4.81 increase in pounds. In simple linear models, it's quite convenient. As I pointed out to you, the slope doesn't change in linear models. So in simple linear models, the marginal effect is equal to the estimated coefficient, which we saw in that Stata output with all the numbers. It equals the slope of the line, which we saw on the graph, and it also equals the derivative of that line. That's the same thing as slope in this case. So let me just pause here for a minute.